Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Routing and access control problems can quietly undermine network performance. They often don't cause immediate, obvious failures, but instead lead to strange application behavior, inconsistent connectivity, or traffic that seems to disappear mid-path. In environments with complex topologies, firewalls, VLANs, and redundant links, it becomes critical to track the actual flow of packets, not just assume the shortest or most logical path. Many issues that don't show up in simple ping tests can only be diagnosed by understanding how traffic is routed, inspected, and filtered at each hop. In this episode, we explore three commonly misunderstood traffic flow problems: asymmetric routing, multicast flooding, and access control list, ACL, misconfigurations. These issues often look like unrelated symptoms at first, but all come down to path integrity. Understanding where and why traffic fails, whether it's due to broken return paths, excessive flooding, or incorrect filtering rules, is a must-have skill for any network technician. We'll walk through the causes, symptoms, and solutions for each, helping you build the layered logic required for complex troubleshooting and exam success. Let's begin with asymmetric routing. This occurs when a packet takes one path to its destination and returns via a different route. While this might seem harmless, especially in redundant or load-balanced networks, it creates major issues when stateful devices like firewalls are involved. Stateful firewalls track session information, expecting response traffic to return through the same interface. If traffic comes back a different way, it may be dropped as unsolicited. This breaks communication even though all devices are technically reachable and functioning. Troubleshooting asymmetric routing requires bidirectional verification. Use traceroute or tracert from both ends of a communication session to see if paths differ. Review firewall connection tables or flow logs to identify mismatched sessions. Monitor NAT translations and state tables to confirm that return traffic is arriving where the firewall expects it. Dropped return packets with no corresponding forward flow are a strong indicator of asymmetry. This is especially common in multi-router environments where devices select different exit paths based on routing metrics, policy-based routing, PBR, or default gateway settings. Asymmetry is often caused by redundant routers that don't synchronize session state, policy-based routing that sends different types of traffic down different paths, or load balancers that don't use session stickiness. In each case, the packet flow seems logical until stateful inspection is applied. The solution may involve consolidating exit points, enabling session sharing across firewalls, or using symmetric routing policies. Understanding that not all traffic returns the same way it left is the first step to diagnosing application failures in redundant environments. Next, we'll turn to multicast flooding. Multicast is a specialized traffic type designed to send packets to a group of receivers without broadcasting to every device on the network. However, if switches don't know which ports have joined the multicast group, they treat multicast traffic like a broadcast, flooding it to all ports in the VLAN. This happens when Internet Group Management Protocol, IGMP, snooping is disabled or misconfigured. The result is excessive traffic, high CPU usage on endpoints, and degraded performance on devices that aren't supposed to receive the multicast stream. Multicast flooding is particularly noticeable in environments that use streaming media, video conferencing, or IP surveillance. Devices that never joined a multicast group suddenly start processing large volumes of irrelevant traffic. This can cause slowdowns, high CPU utilization, and user complaints of network slowness, especially when combined with high bandwidth applications. Monitoring tools may reveal multicast traffic on ports not intended to carry it, or you may see endpoints with unexplained spikes in resource usage. To mitigate multicast flooding, enable IGMP snooping on switches. IGMP snooping listens to IGMP messages between clients and multicast routers and builds a table of which ports have requested specific multicast groups. Only those ports receive the multicast traffic. In larger environments, you may also need to configure an IGMP query A, which periodically polls the network to confirm group membership. Without a query, some switches may fall back to broadcast behavior. It's also important to configure upstream multicast routers correctly so they forward traffic only to the subnets that need it. Multicast problems can be hard to spot without the right tools. Symptoms include media stream buffering, delayed conference audio, or large volumes of traffic visible on unrelated switch ports. Diagnostic tools such as packet captures, net flow analysis, and switch logs help identify unwanted flooding. Once you suspect multicast is the cause, verifying IGMP snooping status and query configuration is the next step. In environments where multicast is intentionally used, these features are not optional, they're required for controlled operation. Switching gears to ACLs, access control lists remain one of the most fundamental and frequently misconfigured network features. ACLs allow or deny traffic based on parameters such as IP address, protocol, or port. They're typically applied inbound or outbound on router interfaces and are stateless, meaning they apply their rules to each packet individually with no awareness of sessions. A common mistake is assuming that ACLs understand context. They don't. They simply match conditions and enforce permit or deny. Some of the most frequent ACL misconfigurations include forgetting that there's an implicit deny at the end of every ACL, applying a rule in the wrong direction, or failing to include the correct permit rule. For example, if an ACL is intended to allow web traffic but only permits port 443 and not 80, HTTP access will silently fail. Similarly, applying an outbound ACL when the relevant traffic arrives inbound causes the rule to be skipped entirely. Even experienced administrators sometimes forget to test ACLs from both sides or overlook address range mismatches caused by wildcard bit errors. Troubleshooting ACLs effectively starts with logging. Many routers support log or log endpoint options that show which packets matched which rules. If logging is unavailable, hit counters on ACL entries can confirm whether rules are active. Begin with a known good traffic source and destination pair, test connectivity, and monitor whether the ACL rules match as expected. If traffic is being denied unexpectedly, check for misaligned subnet masks, incorrect wildcard masks, and ensure that the permit rule is not overridden by a higher perimeter denial. ACL errors often masquerade as routing or application issues, so verifying ACL behavior should always be part of your Layer 3 troubleshooting checklist. When traffic disappears for no obvious reason, an ACL silently dropping packets is a likely cause, especially on border routers or firewalls. ACLs, or access control lists, are processed in a top-down fashion, meaning the first matching rule is applied and no further rules are evaluated once a match is found. This makes rule order critical. If a broad deny rule is listed before a more specific permit rule, the intended traffic will be dropped. Technicians must carefully sequence ACLs, placing more specific permit entries before broader deny entry. A misordered ACL might unintentionally block application traffic or even management access, such as SSH or SNMP. Always document ACL changes and test results to ensure functionality is preserved. ACLs can also interact with other technologies in ways that aren't immediately obvious. When combined with network address translation, NAT, or virtual private networks, VPNs, ACL behavior may change based on translated addresses or encapsulated traffic. For example, an ACL configured to permit internal traffic to a specific IP might block VPN traffic if it hasn't been adjusted to account for the new tunnel endpoint. NAT hides real IP addresses behind translated ones, so ACLs on the outside interface must reference the correct visible IPs. VPNs might encrypt headers that ACLs need to inspect, affecting how rules are enforced unless additional policies or exceptions are created. Modern simulation tools and packet tracer utilities offer significant help when analyzing ACL behavior. These tools can simulate a packet's journey through a firewall or router and identify where it would be allowed or denied. This is especially helpful in environments where the ACL contains many entries and manual inspection is time-consuming. Packet tracers highlight which rule is matched and show whether the packet passes or drops. They can also indicate if traffic is denied due to lack of a match, hitting the implicit deny at the end of the list. Distinguishing between Layer 2 and Layer 3 filtering is also important. At Layer 2, switches may apply filters based on MAC addresses or VLAN tags. These filters are typically configured for port security, VLAN pruning, or security policies like dynamic ARP inspection. At Layer 3, routers and Layer 3 switches use ACLs to filter based on IP addresses, ports, and protocols. When troubleshooting access issues, knowing where the filtering occurs helps avoid false assumptions. A packet blocked at Layer 2 may never reach the Layer 3 ACL, and vice versa. Policy conflicts across devices can compound problems. For example, an ACL on a Layer 2 switch might block broadcast or multicast traffic while the router is configured to permit it. In this case, the traffic never reaches the router for evaluation. Similarly, a firewall might allow inbound web access, but a router ACL upstream silently denies the same traffic. To troubleshoot these complex issues, trace the traffic path hop by hop and verify that each device enforces policies in a compatible way. Even one unexpected drop can break an otherwise functional network. The Network Plus exam often tests your understanding of these layered and interconnected behaviors. You may be presented with a scenario where a user cannot connect to a service despite correct IP and routing configurations. Your task is to determine whether the issue is due to an ACL. Other questions may require selecting the correct command to view ACL hits, explain how multicast flooding affects endpoint performance, or choose the appropriate way to fix asymmetric routing in a multi-router network. These questions reward structured logic and attention to traffic direction and device roles. One of the best tools for catching routing path and filtering issues is logging. Syslog entries can show when ACLs match and drop traffic. Logs from firewalls or routers can indicate connection establishment failures, NAT translation problems, or denied attempts. Reviewing these logs allows technicians to correlate user-reported issues with actual packet drops or mismatches. In stateful devices, inspection logs also reveal when sessions are created, how long they last, and when they are terminated, helping diagnose asymmetric flow issues or traffic that's being dropped for lack of matching return packets. To summarize, complex network behavior often results from misunderstood or misconfigured traffic paths and access control rules. Asymmetric routing can break session-dependent traffic even when routes appear valid. Multicast flooding can overwhelm networks when IGMP snooping isn't in place. ACLs, while powerful, require careful rule ordering, correct application direction, and awareness of how they interact with NAT, VPNs, and other policy mechanisms. These are not edge case topics. They show up frequently in enterprise environments and certification exams alike. Successful troubleshooting starts by confirming where traffic enters, how it's forwarded, and where it's filtered or dropped. Confirm path behavior with traceroute. Review session states and ACL logs. Examine routing and firewall policies on both sides of the connection. Don't stop at a single device. Understand how traffic is processed across multiple layers. That's what separates reactive troubleshooting from proactive, precise network analysis. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.